The development of antibiotic resistance in bacteria is one of the best known examples of how natural selection, acting on random mutations, can produce microevolution at the biochemical level.
The laboratory examples that we can see most clearly, or the examples that we can see most clearly in nature and dissect and analyze in the laboratory, are the evolution of resistance to chemical pesticides and antibiotics in insects and in bacteria, respectively. And what happens very predictably and in a very straightforward way is the evolution of entirely new traits, sometimes by the evolution of entirely new enzymes and compounds. Bacteria, for example, become resistant to penicillin.
In a sense, this is evolution, but it doesn't go anywhere near far enough to really provide evidence for Darwin's theory. For centuries before Darwin, domestic breeders were well aware that they could produce dramatic changes in existing species. And in the case of antibiotic resistance in bacteria, that's all we're doing, or all we're seeing. We're seeing changes within existing species. In fact, just recently, a renowned British bacteriologist said that in 150 years of research, although you might expect new species to appear in bacteria before they would appear anywhere else because bacteria reproduce so rapidly, in 150 years we have seen no new species emerge in bacteria. Well, what Darwin's theory needs is those new species.
Antibiotic resistance, in terms of natural selection, is an excellent example. And its use, I mean, it's one of the hallmark examples given in microevolution for support of Darwinian thought. However, I think in the last few years, it's got to be reinterpreted to a degree.
Laboratory research shows that when an antibiotic is applied to literally billions of bacteria cells in a petri dish, a few mutated cells that happen to be resistant to that drug remain. Those few cells can then give rise to a colony of resistant bacteria. The question is, how well does this mutant strain survive in the long run? This can be measured in what scientists call fitness cost. How well does this mutant bacteria survive when the drug is removed and it now must compete with the original parent bacteria?
These organisms are not able to grow with the fidelity, the robustness that the original parent did, and that's one of the things that we've been looking at. So you can take a culture of cells that are sensitive to the drug, plate them out on petri dishes that have the drug, but there's a single colony coming up that's resistant to the drug. One cell that gave rise to this colony was resistant to the drug out of 4 billion. If this is the parental strain, we now have a mutant, we grow them up separately, and then we put them in the same test tube without the drug. So now we've removed selection, and we can measure empirically the fitness cost in terms of how well the resistant organism can now compete with its parent.
The surprising result is that in a relatively short period of time, the resistant bacteria lose out in their competition with the parent. They can't reproduce as fast and over a short time disappear.
Within 1 or 2 transfers of overnights, you can lose that population of resistant cells. And then after the 3rd transfer, the resistant isolate has been completely outcompeted by the parent.
Why is the resistant strain ultimately less fit? One answer may be that the mutation that produces antibiotic resistance also damages the cell's ability to copy genetic information.
It turns out that the resistant strain has a defect in its information processing system.
So, these bacteria gain resistance to the antibiotic only by losing another key function they need for survival. That's why in the wild the resistant strain would lose out to the parent type, because the resistant strain is actually less efficient overall.
We're going backwards in terms of the fitness of these organisms, not forwards, is used as an example of evolution.
But defenders of Darwin's theory say that's not the whole story. They point out that new mutations can occur in resistant bacteria that will allow them to recover some of their fitness. These new mutations are known as compensatory mutations.
Over time, interestingly, you can find compensatory mutations to increase the growth rate. So second mutations occur to build the organism back to where it was, but they never get back there completely.
According to Minnick, compensatory mutations damage the resistant bacteria in still other ways, again reducing their overall fitness.
So you get locked into this genetic condition that never allows you to recover what you lost initially in exposure to that drug.
The end result is that antibiotic resistance seems to be a dead end for Darwin's theory. It can't generate the types of complex changes needed for macroevolution to occur.